Hello students, welcome to Vista's Learning. This is Shruti D. Nadiga, your chemistry tutor. How are you all doing? Did you have your food? What's there in the food? We have glucose, right? When we eat it, the respiration takes place where the glucose will divide itself into carbon dioxide and water molecules with giving us lots of energy, right? Why I'm speaking about glucose now? Yes, we are speaking about the hydrocarbons where even they also undergo this reaction giving you carbon dioxide and water. We'll study about that in this chapter where we are learning hydrocarbons. Do you remember this chapter? The carbon and hydrogen combine together to form a n number of compounds which leads to the study of its compounds where we call it as hydrocarbons, and here our chapter is. And this is our lecturing class 3 where here we are studying about the properties of these alkenes and some of the conformations. What do you mean by conformations? We'll study. So here we have the first property of these hydrocarbons where they undergo oxidation and gives lots of heat and light energy which we can term it as a combustion. Alkanes on heating in presence of air or dioxygen are completely oxidized to give carbon dioxide and water with the evolution of large amount of heat energy. You can see we have here methane CH4 which is been combining with oxygen to give you carbon dioxide plus water, and here you have lots of energy which is been liberated out. The enthalpy of combustion here is minus 890 kilojoules per mole. If I take the higher hydrocarbons or alkanes, for example butane also reacts with oxygen and gives you carbon dioxide with water molecules, and here the energy liberated during this higher alkane combustion is higher than that of the first one. You can see here the enthalpy of combustion will be is equals to minus 8000 to 2875.84 kilojoules per mole. So a huge amount of energy is been liberated, right? So here you can also find one more thing when we are writing this equation. What is that? The balanced equation, right? When they have been balanced, you can see one carbon atom and 4 hydrogen atom. The molecule has been reacting with 2 molecules of oxygen to give you 1 molecule of carbon dioxide whereas 2 molecules of water. And when I see here 1 molecule of butane will give you 4 molecules of carbon dioxide. Why? Because here in butane we have 4 carbon atoms and that produces all the carbon present in the butane will completely undergo oxidation to form carbon dioxide, and we have 13/2 oxygen molecules which is undergoing oxidation to form carbon dioxide and water molecules, and we get 5 water molecules with a huge amount of energy given. So this can be written in the general formula. So the general combustion equation for any alkane will be given by this, where you can see CN H2N plus 2. This is the general formula for alkane. When this has been reacted with oxygen, what is the amount of oxygen we have to take? We have to take it in oxygen molecule. Nascent oxygen or single oxygen is not been used. So here we'll be having 3N. N resembles to the number of carbon atom which is present, plus 1/2. And this gives you 3n plus 1 by 2 gives you the number of oxygen molecules which has been undergoing the combustion, and that gives you the number of n carbon dioxide plus n plus 1 greater than that of carbon atoms, number of carbon atoms. So n plus 1 water molecule. So this is what we get the general combustion equation. So CnH2 plus 2n plus 2 plus 3n plus 1 by 2 oxygen molecules, which leads to the n carbon dioxide molecule and then n plus 1 water molecule. We can just check this with the previous one. If I am taking here n is equals to 1, then we have 1 carbon dioxide, okay, and this one is 3 into 1, right, because n is 1 plus 1 whole by 2. So it will be 3 into 1 is 4, 3 into 1 is 1, 1 plus 3 plus 1 is 4, 4 by 2 is 2. So we have 2 oxygen molecules, which gives rise to n is 1, n plus 1 is 1 plus 1, which gives you 2 molecules of water. Similarly, when we take this, I'll just write it over here so that you can understand better. If I'm taking C4H10, that is butane, right? When butane is undergoing oxidation, how many oxygen is being required and how many carbon dioxide and water molecules will be given out in complete combustion, we need to say. At this time, you can see that C is having 4, right? 4 carbon atoms. So it will be, the equation for here, it will be 3n plus 1 by 2, right? So we'll be having 3 into 4, that is 12 plus 1, 13 by 2. So 13 by 2 is the number of molecules of oxygen we require for combustion for butane, and it gives rise to 4 carbon dioxide and 4 plus 1, that is 5 water molecules. Got it? The same thing we have here, 13 by 2 oxygen, where 4 carbon dioxide and 5 water molecules are required. So if you know this general equation, any of the butane, you can get the required amount of oxygen for the combustion of that alkane. So as I said, this is the general equation for combustion. Due to the evolution of large amount of heat energy during this, we can consider these alkenes as fuels. They can act as fuels. During incomplete combustion, what happens? We were speaking about combustion. Under combustion, you have two types. One is complete combustion, carbon, which is completely converting into carbon dioxide. Where here we have incomplete combustion, where sufficient oxygen is not being provided. At that time, it undergoes incomplete combustion. So during incomplete combustion, these alkenes with insufficient amount of air or dioxygen, carbon black is being formed. What is being formed? Carbon black is being formed, which is used in the manufacturing of ink, printer ink or black pigments, and also as the filters. So we can see here, when the same methane is undergoing combustion where limited supply of oxygen is being provided, we can get carbon with water molecules, and this carbon which is been got in incomplete combustion can be used for several purposes. Next we have controlled oxidation. So we studied about combustion. Under combustion we have control, we have combustion, incomplete combustion and complete combustion. Here we have controlled oxidation. Oxidation is been taking place, but we are having the catalyst to stop the complete combustion or complete oxidation. That will be called as controlled oxidation. Alkanes on heating with regular supply of dioxygen or air. If you say just air, it is understood that it contains oxygen. So we can just mention dioxygen or air. At higher pressure and in presence of suitable catalyst gives you variety of oxidation products. Here you can see methane when it has been reacted with oxygen in presence of molybdenum trioxide, we get methanal. So this is the aldehyde. We call it as methanal with water molecule, where you can have the ethane because two carbon atoms. Ethane is been reacting with oxygen in presence of acid. We have manganese acetate. When it is been reacted, we get the acetic acid with water molecule. So this is the example where controlled oxidation is been taking place. We have certain catalyst and the temperature in presence of oxygen such that they are not completely converted into carbon dioxide. Instead, they are converted into some other oxide, like we have only one oxygen which is present here. They are been oxidized but not completely oxidized. Okay, so we get methanol, or we have acid or carboxylic acid, ethanoic acid we have, where, or acetic acid, which has been produced during these two products, where we also can have alcohols where it contains OH group, that we'll study. Ordinarily, alkanes resist oxidation, but alkanes having tertiary hydrogen. Tertiary means we know that if you have one carbon atom with all the three or four hydrogen atoms, then it will be called as primary carbon atom. If one carbon atom is been linked to other one carbon atom, then we call it as other two carbon atoms, we call it as secondary. If it is having three carbon atoms on only one hydrogen, we call it as tertiary carbon atom. This is called as tertiary carbon atom. So that carbon atom which is having the tertiary hydrogen atom, tertiary carbon atom linked to the hydrogen atom, can be oxidized to corresponding alcohols by potassium permanganate. In presence of potassium permanganate, this can be removed, H can be removed and OH can be introduced. This is also oxidation. When does it take place? In presence of potassium permanganate or KMnO4. So here we can see methyl propane. Methyl propane, when it is been subjected to the potassium permanganate, it convert itself into 3-methyl propane to all. That means 1, 2, 3. Right? This is the propane. This is 2-methyl. So we'll be having 2-methyl propane to all. This should be 2-methyl, 2-propane to all. So this is how the methane alkane can be converted into alcohol, acid as well as the formaldehyde. Next we have the isomerization. What do you mean by isomerization? They will be having the similar formula, chemical formula, but structure will be different. So the structure can be different or geometrical figures can be different. The orientation of the spatial orientation of the given substances or the substituents might be different. That will give you the isomerization. So in alkenes, on heating in presence of N-alkanes means they should have a long chain, continuous carbon chain. Instead of having the branches, if you have a long chain, we call it as N-alkanes. You can have the example of N-butane, complete chain, continuous chain if you have, then we call it as N-butane. Likewise, N-alkanes on heating in presence of anhydrous aluminum chloride and hydrochloric acid or hydrogen chloride gas isomerizes the branched chain alkanes. That means if you have the continuous chain. This will be converted into branched chain using anhydrous aluminum chloride or in presence of hydrochloric acid or hydrogen chloride gas. So this is what it takes place. It will be the single chain, and when in presence of anhydrous aluminum chloride and the hydrogen chloride, it convert itself into the branched molecule or branched chain. So major products, you will be having two types of products here, where major products will be shown here, and you can also have the minor products. So you can see over here, when we have this CH3, CH2 4 times, that means 1, 2, 3, 4. So 4 times we have CH2, CH2, CH2 because they will be linking like this. And the last CH3 here, this large CH3 here. So it is the hexane because 6 carbon atoms are there, so it is a hexane. When this hexane is being subjected to the anhydrous aluminum chloride and hydrochloric acid gas. So what happens? We get the two major products. What happens here is that the branch has been taken place. So this will be given to one of the carbon atom. You can see here the CH3 will be given down. CH3, CH2, CH, CH2, CH3, and the one more CH3 will be here. That means 1, 2, 3, 4, 5. It will be a pentane. So 3-methyl pentane. So likewise, we'll be having here, this will be CH2 twice here. Here at the end, you will be having one more CH3. I'll write the structure here. This structure, you can easily understand this structure. I'll just write this structure where you have CH3, the CH3 which is attached to the CH, and we have two CH3 group where one more CH3 will be branched like this, and this will be having CH2, CH2 and one more CH3. So you have the difference between this and this. This is, you can see 1, 2, 3, 4, 5, right? 1, 2, 3, 4 and 5 pentane, but the methyl group is attached to a second carbon atom, where here methyl group is attached to the third carbon atom. This is 3-methyl pentane, whereas here this is 2-methyl pentane. So these are the major products which we got from hexane undergoing the branching. How does the N-alkane can be converted into branched alkanes? Using anhydrous aluminum chloride in presence of hydrochloric gas. Next, we have the aromatization. What do you mean by this aromatization? We'll study. So these N-alkanes, again the long chain, have 6 or more carbon atoms. If they are having 6 or more carbon atoms, on heating them in presence of the high temperature around 773 Kelvin at 10 to 20 atmospheric pressure in presence of oxides of vanadium, that is vanadium pentoxide, or molybdenum oxides or chromium oxides, they will support over alumina to get dehydrated and cyclized to benzene and its homologous. This is a benzene ring, as we know. The alternative double and single bond will be present, and the long chain can be converted. Remember, it should be of the length of, I was saying something there. Yes, friends. So as we know, the aromatization, when you have a N-alkane, that will be converted into benzene or benzene-like compounds. That will be called as aromatic compounds. So here we have an example. You can see 1, 2, 3, 4, 5, 6. So hexane is been given here where it is in a long chain. You can also write that in this manner. Okay. this is also the same thing and this is also the same thing, but we have just shifted the bonds here and rewritten like this. So hexane, we can also say it as N-hexane. When it is been undergone this aromatization, we get the benzene ring. What is this? Benzene ring. So what happens in presence of either chromium oxide or vanadium pentoxide or molybdenum trioxide, and at 10 to 20 atmospheric pressure and 773 at temperature, then we get this N-alkane converted to the benzene ring, or a cyclized to benzene ring, or it's homologous. Homologous means if I have one single benzene ring, I can take the other long chain where it is been converted to this other family of the benzene. So we can call it as homologous of benzene. So here hexane, when subjected in presence of oxides of chromium or vanadium or molybdenum at 773 Kelvin and 10 to 20 atmospheric pressure, that hexane can be converted to cyclic structure where we have alternative double bonds, where single and double bonds, single bond and one other double bond, single bond, double bond. Likewise alternative single and double bond, and those are called as aromatic compounds, or benzene and its homologous will be formed in this process. So reaction with steam. When we are going ahead with these alkanes, when they are reacting with water or the steam. So methane reacts with steam at 1273 Kelvin in presence of nickel as a catalyst to form the carbon monoxide and dihydrogen. That means we have the methane. Methane reacts with H2O, which is in gaseous state. That means it is steam at a temperature of 1273 Kelvin to produce carbon monoxide with dihydrogen, that is H2 molecule. So this is how we have the reaction of alkane with the steam. So this method is used in the industrial preparation of dihydrogen of gas. You might have seen this in the hydrogen chapter. In hydrogen chapter, one of the industrial method preparation of dihydrogen is that we take the alkane and it is been reacted with steam to produce dihydrogen. So we have the methane which is been reacting with steam to give carbon monoxide with hydrogen as a gas, or you can also call it as dihydrogen as a gas. And this process can also be called as pyrolysis, giving heat energy and breaking down the hydrogen will get you pyrolysis. The next, higher alkanes on heating to a higher temperature decompose into lower alkanes or alkenes. So if you have a higher alkanes, for example, you have 10, 12, 20 carbon chain, and that on heating at a higher temperature, what happens? They will split into small groups. So we can get alkanes, lower alkanes or lower alkenes. Such decomposition reaction into the small fragments by the application of heat can be called as cracking or pyrolysis. You can see here we have the hexane which is been subjected to the temperature or a higher temperature, where you get the different splitting of them. Here we have the butane plus ethane. Here propane plus ethane plus methane. So this splitting of one compound into several at a higher temperature can be termed as pyrolysis or cracking. So pyrolysis of alkanes is believed to be free radical reaction. Free radical means if you have CH bond, they will be having each one electron will be shared. So they can take back their own electron and become C dot H dot. So this is a free radical. So two free radical, methyl free radical and one hydrogen free radical will be produced, and that undergoes the reaction, and we call that as pyrolysis. Preparation of oil gas or petrol gas from kerosene, oil or petrol involves the principle of the pyrolysis. For example, if you are taking dodecane, a constituent of kerosene, on heating with 973 Kelvin in presence of platinum, palladium or nickel. Why we are taking them? They are the good reducing agents. So on mixture of that we get heptane and pentene. You can see dodecane. Dodecane is carbon 12. Decane means you will be having carbon 10. So dodecane in presence of platinum, palladium or nickel at 973 Kelvin, it gives you heptane, where it is a complete long chain with single bond or saturated compound. We have 7 carbon atoms, so the name comes as heptane. Whereas here pentene, one you will be having double bond, carbon-carbon double bond, hence we get pentene. With that we have some other products also, small products which we can just neglect it. So these are the two main major products. So this is how we can split them and get the other small fragments, and that can be termed as pyrolysis. Next we are going ahead with conformations. What are these conformations? As you see, alkanes contains carbon-carbon sigma bonds. You can see this carbon-carbon sigma bonds will be present in the alkenes. The electron distribution of these sigma molecular orbit is symmetrical around the internuclear axis of the carbon-carbon single bond, which is not distributed due to rotation about its axis. And so what happens? This permits the free rotation about the carbon-carbon single bond. So these carbons can easily rotate on their axis. So that gives you the rotation. That rotation will result into the different spatial arrangements of the atoms in the space, which can change into their one another. Like for example, if I have one carbon atom, other carbon atom, all the 3 hydrogen atoms will be present like this, where we say that it can rotate on its own axis. For example, this is the carbon-carbon atom here. When it is been rotating, one can rotate and one can be stable. What happens at that time? This will change and this will be keep on rotating. So at that time, we can get the hydrogen which is present here will come down, and which is present here will move up, and which is present here will come like this. It will they keep on rotating. So the hydrogen spatial arrangement also differs, and that such spatial arrangements of atoms which can be converted into one another by rotation around the carbon-carbon sigma bond or single bond is called the conformations or conforms or rotamers. What do we call them as? Conformations or conformers or rotamers. So the alkanes can thus have infinite number of conformations. For example, as I take here, I have one hydrogen, hydrogen 2, hydrogen 3. Okay, carbon 1, carbon 2. And I have hydrogen 4, hydrogen 5 and hydrogen 6. So here, this will be stable. I am just rotating this carbon 2. So what happens at this time? The carbon 4 will shift to the carbon 5 and carbon 5 will shift to the carbon 6 and carbon 6 will shift to the carbon 4. So how do we get? Here will the 5 come, here will the 4 come. Right, it will be rotating. So this is different spatial arrangement than that of the before one. Right. So while rotating, we have infinite number of conformations. It is not only they have been stuck here. Instead, if these bonds, if I am taking out and we are rotating, it is not necessary to be here the bond. It can just keep on moving and it can come here. It will be moving and it can come here. N number of spaces it can occupy, right? So at that time what happens? We have infinite numbers of conformations by this rotation of carbon-carbon single bonds. But we cannot consider all these numbers, where it might be remember that the rotation around the carbon-carbon single bond is not completely free. So what happens? It is hindered by a small energy barrier of around 1 to 20 kilojoules per mole due to the weak repulsion interaction between the adjacent bonds. So as we have the adjacent bonds which is been having the barrier, so what happens? We cannot take all the rotations, or all the rotations are not possible. Such a type of repulsive interactions is called as torsional strain. You know the strain, right? In physics you might have studied. Strain means it will be having the opposite force or attraction, or it will be having the hindrance. So here torsional strain will be exerted, or it will be experienced by these bonds. So here we can see the conformations of ethane. Ethane will have CH3, CH3, right? So we'll study about this ethane conformations. So ethane molecule contains carbon-carbon, one single bond with each carbon which is been attached to 3 hydrogen atoms that we know. And the ball and the stick model of this ethane, if you consider, you have a stick like this and one hydrogen. Here we have a carbon and another hydrogen, another hydrogen. This model will be called as ball and stick model of ethane. So this larger circle will be the carbon, and we have small circles which can be considered as hydrogen. So keep one carbon stationary. As I said, one carbon stationary. If we are taking carbon 1 as this, let it be at still. It will not rotate. Only the other carbon rotate the other carbon atom around the carbon-carbon axis. If both are rotating, what is the difference, right? There will be no much difference. So here one will be rotating, one will be stable. So at that time you can see this rotation results in infinite number of spatial arrangements of hydrogen atoms attached to one carbon atom with respect to the hydrogen atoms attached to the other carbon atoms. So that can be called as conformational isomers. You can see here, this is the ethane, one carbon atom with 3 hydrogen atom. And when we are subjecting it to rotate, the backward is been rotating, then you will get a different or opposite orientation as that of the other carbon atom. So this carbon atom was same as like this. Now it is been converted. So this and the before one can be considered as 2 isomers or conformations or conformers or rotomers. This and this, okay? So this has been rotating, and this and the previous one will be considered as the isomers or conformational isomers. So as we see, the many isomers can be possible. We are taking only 2 extreme cases. As we just saw now, it will be of this type and the other will be exactly opposite to that. One will be like this and other will be like this. So these are the 2 isomers we are considering. Okay, one such conformation in which the hydrogen atom attached to 2 carbon atoms are close together are possibly called as eclipsed conformation. So here if you are speaking about the eclipse, this will be called as eclipsed, whereas the other one is called as staggered. So we have these two, where one is eclipsed, exactly one hydrogen, hydrogen 2, hydrogen 3, hydrogen 4, hydrogen 5, hydrogen 6. This hydrogen will be exactly behind this hydrogen 1, and hydrogen 2 will be exactly behind the hydrogen 5, and hydrogen 3 will be exactly behind the hydrogen 6. So this pattern will be called as eclipsed, whereas if they are exactly in the other way, we call it as staggered. So the other in which hydrogen are as far apart as possible is known as the staggered conformations. So first one will be one behind the other. One, if they are very far, then they will be called as staggered. Any other intermediate conformations are called as skew conformations. In between them, will be having the rotation, and at that time we have the conformations, right? Those will be considered as skew conformations. In all the conformations, the bond angles and the bond lengths remains the same, because there is nothing to do with the bond angle and bond length. Eclipsed and the staggered conformations are represented by Sawhorse and Newman projections. To project these two, we have two types, Sawhorse and Newman. So first one is Sawhorse. How does he project that? So if, as I said, if it is having like this, so we have one carbon atom, other carbon atom, slightly slantly we are linking this bond like this, right? So in this projection, the molecule is viewed along the molecular axis. So we are viewing according to the molecular axis, and it is then projected on the paper by drawing the central carbon bond as longer straight line. So this is a longer straight line what we are drawing over here, and upper end of the line is slightly tilted towards the right or the left hand, such that you can have a difference. And the front carbon atom is known as lower end, and the other is the rear carbon atom. First one is the lower end and the other is the rear. And each carbon atom is having three lines, as I show. They will be having three lines, which gives you the corresponding three hydrogen atoms bonding with the carbon atoms. So this is the representation or writing the Sawhorse projection. And these lines are inclined at an angle of 120 degree. As we know, circle will be having 360 degree. 360 degree divided by 3, you will get 120. So each bond, hydrogen and hydrogen, each hydrogen bond will be having that bond angle of 120 degrees. So here is the projection, Sawhorse projection of eclipsed as well as staggered conformations of ethane. So if you see here, this is the eclipsed one. So one carbon atom, when we are writing this wedges, wedges means that it is away from the in front of the plane. The broken lines will say that it is behind the plane, and the straight lines say that it is in the plane. That means if I have a carbon atom like this, it will be in front of the plane. So that will be wedge. If it is behind, it will be broken. And if it is on the plane, that will be considered as a straight line. So here if you see, this hydrogen is exactly behind this hydrogen is exactly behind this, and this is behind this. And that can be given by the Sawhorse projection like this, where 1, 2, 3 and 1, 2, 3. So this gives you the Sawhorse projection. Whereas here, staggered one, you can see the one which is on the wedges, same wedges if you are having on the front or the other plane, opposite plane, it will be opposite now. And the one which is in the behind will be opposite, and the one which is in the same plane will be exactly away from each other. So this is the staggered one, where you can see here, one is the same thing, this is the same one, where it will be the reciprocal of the Y, where here it will be in the form of Y. So this is how we have the eclipsed and the staggered projection of Sawhorse. This is the Newman's, will speak about that. So Newman projections. How does the Newman will give his projection? So the molecule is viewed at the carbon-carbon bond head-on. That means if the bond is like this, now we saw the molecule in this way. So one carbon atom, one carbon atom. Newman saw this like this. The carbon, one carbon, and behind one more carbon is there. So if you have 3 hydrogen atom attached to front and the 3 which has been attached to front and back, it will be like this. So it will be turning like this. In front you can see only the hydrogen atoms, right? Whereas in Sawhorse it was like this. He was showing like this, where you can see all the hydrogen atoms with the carbon atom. So the carbon atom near to the eye is represented by just a point, and 3 hydrogen atoms attached to the front carbon atom are shown by 3 lines as usual and with the angle 120 degrees. The rare carbon atom is represented by a circle. So we will be having a circle which is been given by the rare carbon atom, and that will be having the 3 bonds. Whereas one single point is the front carbon atom and it will be having the 3 hydrogen atoms like this. So this is the front carbon atom which is very small point with 3 bonds, and the circle will represent the rare carbon atom in Newman's projection. The 3 hydrogen atom shown attached to by the rare or the circle carbon atom, will be having the shorter lines than that of the previous one with the same bond angle 120 degrees. So this is the eclipsed one, where you can see this is the front carbon atom and the circle is the rare one, where this hydrogen is exactly behind this, this is exactly behind this, this is exactly behind this. Here what happens is that we cannot just write this is the front carbon atom and I have a circle and I have the hydrogen behind. I cannot exactly write on that itself, right? To have the distinguished learning, to know that that is there, we just write it beside. Over a short distance we are using to say that yeah, it is there. Behind the one more hydrogen atom is there. For that we are using a small space, or else you can imagine that it is exactly on the same position. Okay, this is eclipsed, whereas here this will be having the space, and exact space are given here because this is the one where here you can have the Y shape structure for the back carbon atom, but we are not joining this because this doesn't resembles the Newman's projection. So when we are writing about the staggered, you can just see over here, this is the front one which has been eclipsed and we have the circle. To that each hydrogen atom we have the behind hydrogen atom exactly on the same head on. So we'll have that as eclipsed. Whereas here we have staggered, which has been rotating and we get the hydrogen, this hydrogen coming here. Got it? So this is the Newman's projection. This is the Sawhorse projections. So do you understand this, students? Do you have any doubts? You can see this is the Newman's projection, where you can feel only one carbon atom and the 3 hydrogen is been seamed, but at the back you have the carbon and hydrogen which is been rotating, and we get that as a, this is the staggered, whereas this is the eclipsed, and when it is been turned we get the staggered one. So relative stability of these conformations. In staggered form of ethane, if we are speaking about, So in staggered form of ethane, the electron cloud of the carbon hydrogen bonds are far apart as possible, whereas these minimum repulsive forces or minimum energy or minimum stability of the molecule will be given by the eclipsed one. When the staggered form changes into the eclipsed form, the electron clouds of the carbon hydrogen bonds come together or closer to each other, resulting in increasing the electron cloud repulsion. So which is better than that of eclipsed? Staggered is better or stable. To check the increased repulsive force, molecule will have to possess more energy and thus lesser stability. So as already mentioned, the repulsive interaction between the electron clouds which affects the stability of a conformation will be given as torsional strain. As we know, if we have the hydrogen and behind one more hydrogen, they will be having the reaction which gives you the torsional effect. Whereas if it is at a certain distance, then there will be no electron cloud repulsion, and so they will be more stable in staggered than that of eclipsed one. Magnitude of the torsional strain depends upon the angle of rotation about the carbon-carbon bond. This angle is also called as dihedral angle or torsional angle. Of all the conformations of ethane, the staggered form has the least torsional strain and the eclipsed one have the maximum torsional strain. Therefore, what happens? The staggered conformation is more stable than that of the eclipsed one. So, molecules largely remain in staggered conformations than that of eclipsed one. It may be inferred that the rotation around the carbon-carbon bond in methane is not completely free. Why? Because the energy difference between the two extreme forms is of order 12.5 kilojoules per mole. That means it will be very less amount of energy which is having the difference between staggered and eclipsed form. So we don't have much difference between them. Even at ordinary temperatures, ethane molecules gains thermal or kinetic sufficient enough to energy to overcome this energy barrier, and they can easily shift their projections or conformations through intermolecular collisions, as we have very less difference, that is 12.5 kilojoules per mole. It can be said that rotation about the carbon-carbon single bond in ethane is almost free for all practical purposes. If you are taking other molecules other than ethane, they will be having higher energy which is been provided such that they will be changed from eclipsed to the staggered. But in case of ethane, it is not like that. What happens here is that it has very less amount of energy difference between the two conformations. So they can gain this energy easily by the thermal or kinetic energy. So easily you can get the small energy and you can change from one conformations to the another. So we say it is almost free for the practical purposes to change this ethane from one conformations to another conformation. It is not been possible to separate and isolate different conformational isomers of ethane as there is a very small difference. Hope you are understanding this, students. So by this we finish this session, the conformations and properties of alkanes. Next we'll study ahead about hydrocarbons. Hope you enjoy the class. We Vista's Learning always provide you the quality education for all. For more videos, you can browse into our web application www.v-learning.in. Thanks for watching Vista's Learning.